Oh, hey guys, I wrote a song for you. It's called Physics.
Oh, isn't that cute? Little awkward man playing his instrument for you. So let's take a look at how two otherwise identical Coke bottles, except for the fact that one has a bunch of water in it, might make two different pitches. Anytime a note is played on any sort of musical instrument, the sound is created by something vibrating. In the case of these Coke bottles, it's a column of air. Now, since the Coke bottle is sealed down at the bottom, that's going to produce a close-ended reflection. Anytime you have a close-ended reflection, you have a node there. Up at the top, the bottle is wide open. That means you're going to get an antinode there. When you blow air into a musical instrument, you send all sorts of different frequencies through it. However, the one frequency that causes a standing wave to fit perfectly is considered the resonant frequency. This will cause the entire bottle to amplify its vibration, which causes the sound. Most instruments typically vibrate in their fundamental or first harmonic mode. Now, it is possible to get higher harmonics in there, but often those are simply heard as note overtones. The primary note played, very typically, is the fundamental, especially for simple instruments like these Coke bottles. So, the first harmonic of an instrument that is closed on one end and open on the other just travels from node to antinode, which fits only a quarter of the wavelength inside this bottle. Just for simplicity, I'm going to define the length of my air column as L. If I happen to know the size of my Coke bottle, or the length of the air column vibrating inside of it, then I can figure out what wavelength it is. And since air is the only thing vibrating, I know that the speed of my standing wave is just the speed of sound. Using that universal wave equation, if I know what the wavelength has to be, and I know what the speed of sound has to be, I can figure out the frequency. And for musical instruments, the frequency, measured in hertz, is what determines the pitch that's being played. Now, when I'm playing the Coke bottle with water in it, all of a sudden that length of air column is much smaller. Because water is more dense than air, the closed end is considered to be at the level of the water, not the bottom of the bottle. So that means my connection from node to antinode is much, much shorter. But it's still going to be 1/4 of a wavelength in order to fit a resonant wave inside of this bottle. Now, the exact same equations still apply. However, if my length of the bottle is lower, that means my wavelength has to be lower. But the speed of sound is still exactly the same. So if my wavelength is lower, the frequency is going to have to be higher. With a higher frequency in hertz, you hear a higher pitch.